Swayam Prabha. Digital India. Educated India.
So, let us do some amount of combinatorics. So, it will be a connection between additive combinatorics and this combinatorial geometry or incidence geometry that Arijit was doing. And I felt that Arijit was possibly dealing with the most involved topics in this last week that you have covered, and he really did a good job of doing it, but I would even appreciate it from your side that it was something very abstract that you are learning, but abstract things are not always learned very well just in the class. So, you have to go back, make your hands dirty with things, you have to read up, and then slowly it gnaws it within you, it sort of settles within you. So, what I will do is I will take up a very concrete problem which Arijit stated. So, the problem is as follows. You have a set A over non-zero reals. So, A is a set of, say let us make it non-zero reals, you will understand why this non-zero thing is needed. So, it is a set, mind you say that, so there is no repetition in A. I look at a new set like this. What is it? I take up two elements from the set A, add them up. Mind you, there can be repetitions, then I will store only one of them. Fine. Similarly, I define this set. Is a product set. Fine. Okay. Now, if I ask you something about this cardinality of this A plus A and ask you when can you expect this cardinality to go down. So, this is a question for you. I told you I will ask you, no? So, you understood the problem, no? At least I will try to make you understand the basics of the problem. You have a set of non-zero reals and you look at this set where you pick up two elements, right? It is a set, so no repetition, and then you build this set A plus A, and similarly you build this set A product A. And the question is, when will the cardinality of this A plus A be minimum kind of, cardinality is means the number of elements in the set. Yeah, when, I mean, can you think of how these numbers are, such that the cardinality of this will go down. So, there will be less number of elements. Wait, hold on. You know arithmetic progressions, no? Okay, let's. Okay, fine. Yes. When can that happen? Intersection between two sets. Where did you get two sets? There is only one A. So, did you understand this problem, no? Say A has 1, 5, 6, then A plus A has what? What are the elements in A? 6, right, 11, 7, right, fine. Right. So, there are fine, okay, maybe. Now, the point is if you, so this is the way this set is going to be generated, no. So, you look at all pairs and you add them up, and I have even not put this restriction that A1 A2 has to be distinct. Okay. My claim is if the numbers are in AP, then there will be many such repetitions, no. You will not get kind of, because otherwise you are looking at all pairs of numbers roughly quadratic, right. So, if the numbers are in AP, then some of the sums would collapse to the, right, that is an observation. But if A is in AP, then what happens to A dot A? Then there are not going to be almost any repetitions in A dot A, no. So, then what happens is, while trying to push down A plus A dot A might go up. Similarly, if you want to minimize this A dot A by putting the numbers in geometric progression, then A plus A might shoot up. So, what I now want is, I want to sort of argue on simultaneously, if I want to minimize both, what can be its kind of cardinality. So, I will look at the cardinality of A plus A dot A, I will take the maximum of them and I will try to show to you a lower bound of that. So, I will try to show you that this cardinality, that the max of these two should be at least greater than equal to something. A simple combinatorics problem, fine. The answer will lie in what Orijit talked to you in incidence geometry. Okay. So, let me so the basic backdrop of the problem is clear to you. Okay. So, let me now first formally define the problem because I will talk of a proof. So, let us be a little bit more formal. So, A is this non-zero reals, your A plus A is as I defined A1 plus A2, A1 A2 belongs to A and your A dot A is so now define max of the cardinality of these two. So, I essentially want okay. So, essentially we want to find a lower estimate of G n, and the theorem that we are sort of aiming at is max of say I will give you a lower bound, that it will be at least as big. So, we will find a number here. So, this would be kind of a function of n. So, we will figure out that bound that if you take the max, it would be max of both, it would be at least as big as that function that we are going to fix very soon. Okay. So, the problem is clear. Any doubts about this, understanding this problem? Oh, sorry, I am very sorry. Yeah, correct. You are following, no? Good. Yes. Yeah. If you have not understood it, forget it. I mean, so what I am doing is looking at all A's of cardinality n, and so essentially it's the result is not on the set A, but on the size of the set A, right. So, that is why I did bring it in, but if you are not appreciating this, do not bother too much of it. My theorem statement has nothing with G. So, essentially I say that this so it's what is this? This is a lower bound, no, that this will be at least as big. So, it will be greater than this, right. So, what I did was max, the max is greater than this, you cannot minimize it beyond this quantity, agreed. So, the problem statement is clear to everyone, right. So, this is the last talk of this week. So, I want everyone to understand. If you have doubts, raise your hands, ask me. No, okay. Now, then just forget about this problem. We will come back to it again. Let us now sort of quickly do a recapitulation of what Arijit did, that would help us. First, he did this crossing lemma, no. What was the crossing lemma? What was the crossing lemma? For a graph having suitably many edges, you cannot avoid a certain number of pairwise edge crossings, right. So, if you want to draw a graph with a a suitably dense graph with a certain number of edges, then you cannot avoid some crossings, okay. And you have a formal statement of it, and that he used by doing a nice probabilistic argument. But the statement, let us sort of recall, we just take this lemma, we are not going to prove it now. I think you already know the proof, or you can just look back. This is important, remember, it is a simple graph. Or you can see from the back. Okay. For any simple graph G, remember, I mean, whenever you apply crossing lemma, ensure that the graph that you turn out with needs to be simple. This is a very important thing for crossing lemma. So, for any simple graph G with capital N vertices and E to be greater than 4n edges, the crossing number of G is at least some constant into E cube by n square, right. So, this is proved by making a probabilistic argument. Now, if you see, this is telling you that for a dense graph, E would be E cube would be roughly kind of n to the 6, no. If you have suitably all kind of at least a fraction of all possible edges. So, it is giving you a very kind of a nice bound, no. Okay. So, this was crossing lemma, and he did for you using crossing lemma one of the fundamental results, which is known as the, I find a little bit difficult in pronouncing this name, but Zemeredi. Okay. And I think there is a, so it is known as the Zemeredi-Trotter theorem. So, the version of Zemeredi-Trotter theorem that Arijit did is as follows. So, I will try to keep this notational consistency. So, capital N would be vertices for me, small e would be edges for me. Okay. So, the version that Arijit did was for n points, and so I am using my notation, but essentially this was it. For n points and m lines in the Euclidean plane, the number of incidences, remember what was incidence? Line point pair, no? Okay. The number of incidences among the points and lines is at most some constant c right. So, I mean, though I am writing the same c again and again, but each constant would be different in the context, no, because if I make C1, C2, it will be sort of messy. So, our constant is a constant in that context, fine, because constants can vary around from lemma to lemma theorem. So, I mean, though I have written this C and this C to be the same, but they are essentially different constants. Okay. Fine. So, this thing he did. So, how did he do this? To do this theorem, what he did was, he so assume, I mean, without loss of generality, that a line has at least one point on it, right, otherwise there is no incidence. So, what he did was, for each point on this line, think first, forget about the lines, think of the points as vertices of your graph, right. Then what he did was, he considered those lines, and the edges in the graph were formed in the following way. On a vertex, rather on a line, if you had two vertices side by side, they are giving an edge. So, this way the number of edges was formed. So, in the edges you sort of get roughly, if you think of say L points per line, you would have got L minus 1 edges. So, in all L minus 1 edges into, you multiply it with m lines, you would roughly get the number of edges in this graph, and you know that there are lines, right. So, two lines cross at most one point. So, you could figure out the number of crossings in this graph bounded by n square, and then he plugged in this value to show to you a bound like that, fine. That was the proof idea. Okay. Now, see, I mean, whenever you are applying crossing lemma to prove a thing, essentially the idea is form a graph such that you can form a graph using such suitable geometric structures, so that you can quickly figure out what is the crossing in that graph, right. Now, you will have a vertex or an edge fixed for you, and the other one you estimate. If you look into this, there are three terms, no, the crossing, the number of edges, the number of vertices. What you want to estimate in that particular problem, say in here you have Zemeredi-Trotter, somewhere you will have unit distances, but whatever you want to estimate, that will be one of these three parameters, rather one of those two parameters, and the geometric structure that you impose on the points or lines, that would determine what your crossing number is. So, there would be one variable left to estimate, and that would sort of give you the bound. So, this is the idea of applying crossing lemma to get different kinds of bounds in combinatorial geometry. So, what I would do is, for me, I would need a different variant of Zemeredi-Trotter, which Arijit did not prove. So, this version of Zemuridi-Trotter would have the following restriction. It would ask of you that each line should have at least some many points. So, I will sort of put a density requirement on each line, that these lines would have at least this many points, and then again deduce Zemuridi-Trotter. Okay. So, let us first look at this statement of the theorem. I mean, this theorem can follow as a corollary of the previous the general form of Zemuridi-Trotter, but we will go through a proof of it, because to make sure that everyone understands the final proof. So, the statement of the theorem is this. So, you can think of this as even a corollary of, and this was even done by Zemuridi-Trotter. I usually forget where to put that. Oh, it is over the E, no, this E or no, last E. So, corollary of Zemuridi-Trotter. So, let so, if you look into this variant of Zemuridi-Trotter, it was just talking of incidences in terms of points and lines. What this says? This also says a story like that, but sort of takes, looks at the number of, bounds the number of lines. Okay. So, first, so just sort of allow this theorem to sink in you, what it is telling. It is telling that now each line in the Euclidean plane should have at least this many points. Okay. So, I will just forget about the other lines. So, the lines only that have this many points and n is this number of points. So, I want to it will be at least 2, at most square root n. So, if you have this many points, at least this many points, then the number of lines is upper bounded by this. So, let us look at a proof of it. So, the formation of the graph is just the same as in the previous proof of Zemuridi-Trotter, but only you take those lines which have at least t many points, fine, and then the construction of the graph is same. You have this line, you have vertices on the line, vertices are points are vertices, and if 2 points are side by side on a line, you give a edge. And if you know there are m lines, there would be roughly m square kind of crossings. So, let us go through the proof of this. So, what you do is construct the graph, should I just say as said? No, let me even write it. No. No. Okay. Fine. So, what is going to be my number of edges in this graph? M lines, right, t minus 1 edges per line roughly. So, this is going to be equal or more than this, no, agreed, no doubts about it, fine. Now, what will happen is, now see the way I have formed this graph, there is no guarantee that this number of edges is more than 4 into capital N. This one, M lines, each line has t points. So, the way I formed the edges was like this, no. So, these were my edges. These were my edges, no. Agreed now? T points are on the line. So, per line you will have t minus 1 edges, M lines. So, at least m into t minus 1, rough counting. Okay. Right. Now, I have no hold on this E, no, because I have forgotten about some lines and some points, some incidences I have forgotten essentially. Now, this would be an hindrance to apply this crossing lemma, because in crossing lemma I need this condition. Okay. So, what I will do is I will do two cases, one case in which crossing lemma can be applied, then I use the crossing lemma. In the other case, obviously your number of edges would be less than 4n, but when your number of edges would be less than 4n, remember I have a condition which I have not used till now, and that is this condition. This condition is telling me something about capital N and T, right. So, we continue the proof. My first case, is that crossing lemma holds. Okay. So, that is the case 1, and then it is easy to see that if this has really, if this has held, then just plug in the value of E. Okay. So, you have m cube t minus 1 cube by n square. No? So, what I just do is remember E was remember E was greater than equal to m into t minus 1. So, you just now solve it to get m to be less than equal to c into n square by t minus 1 cube, suitably change the constant to get some constant c n square by t cube. M square is your number of crossings, no? So, in this case your crossing, so you had crossing to be greater than equal to some c into e cube by n square. Okay? So, I have even counted over counted, no, m c 2. So, I have even taken something more. So, it is m square greater than equal to this. Agreed? Any doubts? What? Right. Right. So, I have even put something more, no? Think of this as an equality, no? So, that is the way I count edges, no? Let us do now case 2. So, you think of the edge as equals to m into t minus 1, no? Now, let us do case 2. So, case 2 is about E number of edges less than 4n. So, it is m into t minus 1, which is going to be less than 4n. So, you have now you invoke this condition that I said. So, m is less than 4n by t minus 1, and you can see this that because your t is less than square root n. So, square root n by t is greater than equal to 1, and so your n by t square is also greater than equal to 1. So, you multiply this with something greater than 1, no, 4n by t minus 1. So, you multiply it something with say with a constant that is greater than 1, and you replace this one, no. So, you can write n by t square here, and that would again be this some constant into n by t cube, sorry, square. Fine. Just applied crossing lemma. So, P implies Q, and when that P failed, so we did both cases, right. So, we have also proved Zemredi-Trotter, and as I said, I mean, though this is a new proof, this even follows from a corollary of the original one. Okay. Now, we have something in. So, what is now it? So, like related to numbers, real numbers maybe, and we have combinatorial geometry. What is the connection? What? Right. Right. What is the connection? Right. That is what we are going to explore. Numbers, sets, geometry. Right. Now, what I am sort of trying to impress upon you is it helps to do geometry. If you do geometry, you can solve robot motion planning, you can do approximation algorithms, you can do combinatorics, you can even solve problems in number theory, right. So, geometry is a very rich tool and sort of trying to oversell geometry to you, so that you feel interested and think of doing geometry. Okay. Now comes the punch. Now, this punch is a paper in Acta Arithmetica by Georgi Gelelekesh. It is just a 2-page paper, and the proof is really this much. Let us do the proof. It was around 1997. I mean, see, many of these problems in number theory or in combinatorial geometry grew out of many of the questions asked by Paul Eddosh. So, this was also one question asked by Paul Eddosh. I mean, he was kind of a genius. I mean, he asks very simple looking questions, and this gives rise to different kinds of theories, connects theories here to there. It's like brilliant things. Okay. As a human being, is also he is like such a great. He was an Hungarian mathematician. Okay, let us now connect. Now, to connect, what I have to do is I have to bring in what? Lines and points from numbers. The way I would do it is as follows. I would sort of look at a 2-dimensional grid on whose one side would be this set A plus A, the other side would be this, right. So, my points would be points would be like H k, where H is in A plus A and K is in A dot A, right. So, think of a grid like this, fine. And what I try to estimate for you is, so so what you are looking at is points like this, grid points like this. I am drawing it in an arbitrary fashion. So, grid points like this. So, what I will try to do for you is I will try to estimate this total cardinality for you. So, what I will do is I will define some lines over this point. So, that is kind of a function, and I will ensure that those lines contains at least some many of these points. Okay? And if I can estimate that cardinality, say it is something, say some capital M, that this cardinality, then its maximum should be greater than because looking at a product of two sets, right, and I have showed to you that this cardinality full is bounded by some m, then the maximum of it should be greater than equal to square root of m, and that is what I wanted to do, max of A plus A and A dot A, agreed. So, I will take, so this is your connection from numbers and sets on numbers to geometry. Which one? M of the cardinality of the number of points here, right? This, how many of this type of points are there? I will try to estimate that, right? Then the maximum of it would be greater than, agreed? So, this is the technique. So, what I will do is now, so points are there now. So, I have to now bring in lines in some way, and I have to ensure that these lines that I draw contains at least some points from here. Then I can apply this theorem, fine. I need this condition, remember. So, I have to bring in lines for you which contains at least that satisfies that condition, and then I can play around with this bound, agreed. Okay. So, what I will do is I will ensure that I can estimate from my transformation from sets of numbers to geometry is, I will estimate M and T from my geometric construction. So, then N would be one inequality, one variable, N would be estimated. So, that would be my idea. Now, the trick of LHS's paper is as follows. So, now let us talk of the proof. So, we start with again the same thing. So, the punch line will come in defining a function that will take you from a plus a to a dot a. This is just this does it. Why does this do it? Pay your attention here. Pay your attention here. This is a linear function, no? So, what I am doing is I am taking pairs from here, I am taking numbers from here, pairs of numbers from here, and I am forming a linear function out of them. I need two things, y equals to mx plus c or whatever, right, and this is my linear function. Now, put x equals to what do you get? Good. Right. So, it takes you from, so this function takes you from a plus a to e dot a. Okay. Okay, so, I sum this in a lemma So, essentially what is happening is A k plus A I goes to A j dot A I, which essentially belongs to this for every A I belonging to A. Right, that is what we wanted. So, what is this telling me? It is telling me that this linear function that I defined, which was f j k sorry x equals to A j into x minus A k. So, you plug in an A I, right, there can be n different many. So, on this line, so this pair is fixed, a line is fixed. On this line for n of different A I's, you get them to be lying on this line, agreed? Okay. Which one? Look into this. What is this telling you? This was a linear function I defined. Now, just forget about this. Oh, sorry, this does not work. I was hiding this and thinking that first do not look at this part, just look at this linear function. This is a line, right. So, defined for all these x's. So, what I do is I plug in x equals to a k plus I. J k is a pair. So, you look at all pairs form line like this. How many? Look at all this, all possible pairs. Fine. So, you are forming n square such functions. So, n square such lines, right. What is the property of each line? Mind you, what I wanted, that each line should contain at least some many points. Now, does all of these n square lines satisfy that property? It does, because if you replace x equals to a k plus I, mind you this was your x, no, this was your x, this was your x, no. If you replace a k plus I, which is a value here, in this function, you get an element like this. That is what a linear map is, agreed. So, on this line how many points are there? At least as many A I's are there. How many A I's are there? N. So, each line now contains at least n points. We are in the domain of Zemredi-Trotter, no? What did Zemredi-Trotter need? What did this theorem need? Now, we can come back and look at Zemredi-Trotter. It needs that for n points in the Euclidean plane, the number m of lines containing at least t many points is something, no. So, I needed all my lines to at least have some many points. This I have ensured. Each function, each one was a line. We have n square lines and each line has some many points, n many points, agreed. Now, just apply Zemredi-Trotter. So, even to give you, so maybe this note would help you if you still have doubts. Sort of summing up what I said. So, I have shown to you that each line contains n many points, no, of which point set? Let us call that point set to be P, that is surely this point set, right. What is its cardinality? This is the set, I mean if you talk in terms of set, sorry, right. This is the set of points. So, what I now do is put so how many lines do I have? N square. So, my m is equals to n square. Each line has at least n many points. So, my t is equals to n. Now, does this t satisfy the condition of the lemma? Look back. This t does, no? It has to be less than square root of the number of points. Okay. Yes. Apply summary the trotter. So, if you solve this, you have capital N to be greater than equal to C minus half n to the power of 5 by 2. So, just plug in and solve. As I said, all this kind of this crossing lemma based proofs of, or rather if you look into these theorems, there will be essentially 3 terms. You estimate 2, rather by your construction you fix 2, then you get the estimate of the third one. Now, mind you, you had agreed. So, what is capital N? N is this total number of points, and you had already agreed that the max of these 2 would be greater than equal to now square root m. So, if you go back, this should be some constant into n to the power of 5/4. Done. Do not you find this to be cute? I repeat, the problem definition is clear, fine. What you just need to understand is this version of the Zemmelweis-Trotter theorem, which you can go back and see. The only thing is, this version of Zemmelweis-Trotter you can apply if lines has at least few many points. So, go through the proof. Now, the connection is important, and this connection is nothing but setting up a grid which is grid of size which is the product of cardinality of this and this, agreed. Then the max of these two quantities, this and this, should at least be greater than equal to the points in here, right, no doubts about it. Now, what LHS does is he brings in lines, points are already there, points are already well defined, no, once the set A is there. So, A plus A and A dot is defined. So, the grid, each point of this grid is well defined for you. How many of them are there? The product of these two, fine. Now, he brings in lines by this. Now, when he brings in lines, he ensures that the function, that this linear function is such that it contains at least some of these points, so that he can apply Zemre-Trotter. That was just the trick. So, if you could also think of such a nice linear function, the proof was yours. And then this linear function shows you that for any ai, so you fix a jk pair. So, there are n square such lines, right, and mind you, I had estimate on the cardinality of the point set, this grid. I have an estimate on these lines, right. Now, see what essentially happened, your lines came from the set A, no, the cardinality of the set A was n. So, your number of lines came from the cardinality of that set, your points came from the product of these two sets, and the trick was to define the lines in such a way that they vanish for at least n many of them, right. So, now you can fix that per line for each one of these n square lines, it has at least n many. Now, just apply Zemre-Trotter, and once you apply Zemre-Trotter, this bound is there for you, and then you apply that square root m or whatever that thing we discussed, no. So, from here it is an easy consequence, the final bound is an easy consequence. The consequence we had discussed earlier, no, this. So, this is the easy consequence. The max of this should be at least greater than the square root of the number of points there. It is kind of magical, no. Sushovan, which one was better? Say loudly. Thank you. Yes. So, I proved on all reals, no. So, set A had all non-zero reals. Now, if you take special kinds of numbers, maybe you can play around with the bounds a little bit. A
dot A is different for all the pairs.
So what? I mean, see, I assume nothing on these numbers, no? They are just real numbers, just non-zero reals. Did I assume anything on these numbers? You can make special kinds of numbers, but then you have to work out through this bound.
I am assuming this to get the upper bound for that. So the upper bound.
Oh, that argument I am not making. I am making a lower bound argument. So, the essential, I mean, I started by saying that one can get big at the cost of the other, no. So, it is like if I was trying to minimize one, the other was going up. How much? That maximum I sort of bounded, that it has to go at least this. Yeah.
Can elements be equal in the set A?
No, it is a set, no. I was harping on this at the very beginning. It is a set. So, set cannot have multiple occurrences of the same element. You study sets from quite a young age, no. In my time, set was in undergraduate times. 11, 12 also I did not know what is a set. when I say and even I harped on that. Any more? Okay.